Continuing with UV spectroscopy, when we try to look at the structure determination of aromatic compounds, the scenario is a little different. Although aromatic rings are among the most widely studied chromophoric group, the absorption that arise from various electronic transitions are pretty complex. On first inspection, benzene has 6 pi molecular orbitals, out of which 3 are filled and 3 are unfilled pi star orbitals. Now, as the picture would depict here, that these pi 1, pi 2, pi 3 are the filled orbitals and pi star 4, 5 and 6 are the antibonding molecular orbitals, where the transition of the probable electron is possible. In general, the general features of aromatic compound, one would expect there to be 4 possible homo-LUMO pi to pi star transition at observable wavelengths, that is because of the conjugation. Due to symmetry concern and selection rules, the actual transition energy states of benzene are slightly different, and therefore, there are some forbidden transitions and there are some allowed transitions. The allowed transition is at 180 nanometer, whereas the forbidden one are at 260 and 200 nanometers. So, that shows that from pi 3 it cannot go to pi 4, from pi 2 it cannot go to pi 5. So, these are the forbidden zones which are not allowed, but from pi 2 it can go to pi 4, from pi 3 it can go to pi 5. So, these are certain allowed transitions and there are some forbidden transitions, although the wavelength may be higher, but yet these symmetry rules and symmetry concern and selection rules hold good for aromatic compounds. In general, if we try to look at the molar absorptivity also, it is found that the allowed transition has a molar absorptivity of the order of 47,000 and is not the routine range of the UV at 180 nanometer, as referred to as the primary band. The forbidden transition, which has a molar absorptivity at 7,400, is observed if substituent effects shift it into the observable region. This is referred as second primary band. At 260 nanometer is another forbidden transition, which has a molar absorptivity very low, that is 230, and is referred to as secondary band. This transition is fleetingly allowed due to disruption of symmetry by the vibrational energy states, the overlap of which is observed in what is called the fine structure. So, you see there are various types of bands and sometimes very fine structures, that zigzag noise type of thing is also seen, which is due to the secondary band. But the main observable and the graph that is, or the spectrum that is seen for aromatic compounds is mainly in the region of 180 nanometers, and it has a very good molar absorptivity, that means the peak will be fairly high. Now, in general, substitution, oxochromic group presence, conjugation and solvent effect can cause shifts in wavelength and intensity of aromatic system, similar to dienes and enones. We just saw that because of the presence of a substituent, because of a presence of an oxochromic group, or due to enhanced conjugation, that is double bond, single bond, double bond, there is a possibility that the wavelength will shift and it will also affect the intensity of the peak. So, these rules hold good. However, these shifts are difficult to predict. The formula of empirical rule is for the most part is not efficient, and therefore, there are some exceptional rules also in this case. There are some general qualitative observations that can be made by classifying substituent groups on the benzene ring. Now, substituent with unshared electron, if a group attached to the ring bears n electrons, that is the lone pair electrons, they can induce a shift in the primary or secondary absorption bands. Non-bonding electron extend the pi system through resonance, lowering the energy of transition between pi to pi star. So, because of their contribution, you see the lone pair on the G, actually that is the group, is actually participating with the ring, and therefore, the electronic densities at the ortho and para positions are enhanced. Therefore, the pi to pi star will also face a lowering of energy. More available lone pairs or n electrons, the greater is the shift. So, the more the number, the more will be the contribution and lower will be the energy requirement, because the ring is getting enriched from the outside source, or that is the participation of the lone pairs. So, these are certain things which need to be remembered. Even the substituents have a effect on the ring. The presence of n electron gives a possibility of n to pi star transition also. If this occurs, the electron now removed from G becomes an extra electron in the antibonding pi orbital of the ring. This state is referred as charge transfer excited state. Now, what happens? The electron from the lone pair is now coming within the ring, and therefore, the ring is having an extra electron, and the group is devoid of one of the electron which has got excited, and therefore, these also participate in the antibonding clouding of the antibonding orbitals. So, this is a very typical case where the substituent plays a participatory role. The substituent effect, substitutions or substituents with a unshared electron, pH can change the nature of the substituent. Deprotonation of oxygen gives more available n pairs, lowering transition energy. Protonation of nitrogen eliminates the n pair, raising transition energy. So, suppose if pH has to be altered, what all can happen to the substituent? If it is an oxygenated substituent, then deprotonation may take place, or if it is a nitrogen substituent, then protonation of nitrogen can also take place, but they will have opposite effect. By deprotonation of oxygen, more it will be more available, the lone pair will now be available into the ring, and therefore, there will be a lowering in the transition energy. However, if an amine group is protonated, what will happen? The lone pair is already reacted. So, it is not available for the ring participation. Therefore, there will be a raising in the transition energy. So, if you try to look at the primary and the secondary effects of these, if there is a simple substituent H, the lambda max is 203 and the molar absorptivity is 7400. And if it is OH, it is the lambda max is 211 and the molar absorptivity goes down. If it is O minus, the lambda max goes up and the molar absorptivity also goes up. If it is a simple amine NH2, then the lambda max is 230 and the molar absorptivity is 8600. But if the same amino group is protonated, that is NH3 plus, then the lambda max reduces to 203 and the molar absorptivity also reduces. So, it is all related to what is the situation of the substituent, whether it is a heteroatom, and if the substituent is a heteroatom, there is a possibility of the lone pair to participate, but due to pH alteration, it can either get protonated or it can get deprotonated, and both will have a reverse action on the transition energy of the transition state. Therefore, substituents play a very major role in the aromatic compounds, substituents capable of pi conjugation. Now, if there is a possibility for pi conjugation, even then substituents play a very important role, because they can interact with the pi system of the benzene ring. With benzoic acid, this causes an appreciable shift in the primary and secondary bands. So, now we have seen that aromatics have two types of bands, one is the primary band and the secondary band. So, it will affect both in the case of benzoic acid. For the benzoate ion, the effect of extra n electrons from the anion reduces the effect slightly. So, if we try to look at a simple benzoic acid, the lambda max is 230 and the molar absorptivity is 11,600. If we look at the benzoate ion, it actually goes up, because now O minus is now participating with the ring and the lambda max goes to 224, but the molar absorptivity goes down and it is now 8,700. So, you see the primary bands are really affected drastically, looking at the condition of the acid and its salt. If the substituent has an electron donating or an electron withdrawing effect, then what will happen? No matter what electronic influence a group exerts, the presence shifts to the primary absorption band to a longer lambda. Electron withdrawing group exert no influence on the position of the secondary absorption band. Electron donating group increases the lambda and the molar absorptivity of the secondary absorption band also. So, you see that both primary and secondary bands are in a way affected, whether there is an electron withdrawing group or an electron donating group, because if there is an electron donating group, it will increase the densities at the ortho and para position, but if it is a electron withdrawing group, it will make the meta position slightly higher in electron density as compared to the ortho and para, and therefore, they will have their own effect on the primary band and the secondary band. So, these things, these are very, very intricate information that one should have an understanding while calculating the UV of a predicted sample, and therefore, it is possible to do that, because structure determination, one can predict what would be the wavelength approximately, and it has been found that by Woodward-Fieser's rule, the calculated value of the lambda max has been found to be for a very large number of compound similar, very close to each other and sometimes even the same. Now, substituents which are electron donating and substituents which are electron withdrawing have certain effects, and you can see that if you look at the electron donating substituents, the lambda max goes on increasing, and but however, it does not make much of a difference on the molar absorptivity. However, if you see electron withdrawing group, again the lambda max may increase or decrease, but molar absorptivity goes down drastically in the case of electron withdrawing group when we consider the primary band. That is not so much of a effective situation in the secondary band, but there are changes. The lambda max does change, it increases as we go down the electronegative series of the electron donating groups. Similarly, if there are di substituents or if there is a multi group effect, everything is going to make a difference in the electronic environment of the molecule. With di substituted aromatics, it is necessary to consider both the groups. You cannot say that only one group is participating. Why? Because the group both the groups are in conjugation with the benzene pi rings. So, if they are in conjugation, they will participate with each other and will have a collective effect. If both groups are electron withdrawing or withdrawing, the effect is similar to the effect of stronger of the two groups, it may be said that it is a mono substituted ring. If one group is electron withdrawing and one group is electron donating and they are parallel to each other, the magnitude of shift is greater than the sum of both the groups that can effect. So, if we try to look at an amino group attached to the ring and at the para position there is an electron withdrawing group, that is the nitro group, what will happen? Everything will be in conjugation as shown in the slide. Similarly, there are other effects that can be discussed. Dye substitution can also have a lot of effect on the electronic situation of the molecule. If the two electronically dissimilar groups are ortho or meta to each other, the effect is usually the sum of the two individual groups, and we call it meta no resonance or orthosteric hindrance. So, if they are at a meta position or at ortho position, the two electronically dissimilar groups, then they will have an effect on each other. For the case of substituted benzoyl derivatives, an empirical correlation of structure with observed lambda max has been developed. This is slightly less accurate than the Woodward-Fieser rule, but can usually predict within an error of 5 nanometers. So, now there are some assumptions, there are some calculations which have been tested for such dye substituted effect participation in the structure determination of aromatic compounds, but then there is a level of error also possible, and the level of error or the difference in the calculated and the experimental value can be as high as 5 nanometers. So, this has to be kept in mind that it is not as accurate as the Woodward-Fieser rule, which we saw for the acyclic compounds or the non-aromatic compounds. So, several examples have been given what is the parent chromophore, and the parent chromophore will have a basic lambda max. Then to that, with the group that is attached, more and more increment of the substituents can be added, and a total of the final substituent and the calculated wavelength can be ascertained. Now, when we try to look at the aromatic compounds, the polynuclear aromatics, when many benzene rings are or more than one is present and the benzene rings are attached to each other or fused to each other, like in the case of naphthalene, phenanthrene and so on, then what happens to the UV spectrum? When the number of fused aromatic ring increases, the primary and the secondary bands also increase. So, you see the primary and the secondary bands are associated with aromatic compounds. When they are associated with aromatic compounds, if the number of rings are increasing, then they will definitely contribute to both the primary bands and the secondary bands. For heteroaromatic system, spectra become complex with the addition of n pi star transition, and ring size effects are unique to each case. So, you see that when it is a double just 2 rings, that is naphthalene cases, the spectrum looks like the pink one. When it has 3 rings fused to each other, the spectrum looks like the green one, and when it is 4 aromatic rings fused to each other one after the other, the spectrum moves more towards visible region, leaving the UV region, and it becomes it is shown in by the blue lines. Now, so far we were trying to understand the UV spectroscopy and how to determine structure with the help of UV spectroscopy, what does a lambda max indicate, how to interpret and calculate lambda max, and then compare with the unknown. Now, let us try to apply it to visible spectroscopy also, because UV goes hand in hand with visible. Although the visible range is very small as compared to the UV range, but still it is important to understand the portion of electromagnetic spectrum from 400 to 800 nanometer is observable to the human eye. We and some other mammals have the adaptation of seeing colors at the expense of greater details. So, you see that the visible region is extremely small region, just between 400 to 800 nanometers, and this region is perceivable by our eyes and eyes of some of the other mammals. And so, it has been divided into different colors: violet, indigo, blue, green, yellow, orange and red, and we call it VIBGYOR. As we all know that this is the color range of the visible region. Now, when white light, that is continuum of the lambda max light, passes through or is reflected by a surface, those that are observed are removed from the transmitted or reflected light respectively. What is seen is the complementary colors, those that are not absorbed. This is the origin of color wheel. So, what we see is actually the complementary color. So, the one which is actually being absorbed is not seen by us. So, that should be very clear that light, when it passes through on a reflected surface, some of this is actually absorbed, and when it is absorbed, the transmitted light will be devoid of that portion of light which has been absorbed, and what we see is what is reflected. So, it is the complementary, that substance which was not absorbed or the light part which was not absorbed was actually seen by us, and that creates a color wheel which have different wavelength regions as shown here. In general, when we see a colored compound, we try to understand how the structure must be of this, because the moment it comes to the visible region, it must be understood by the analyst that it has a fairly large number of conjugation to push it from UV region to visible region. Any colored compound must have a substantially large area of conjugation of double bond and single bond. Only then it will be pushed to the visible region. If it has only one isolated double bond or just two bonds, it will be colorless and it will remain in the UV region, not in the visible region. First thing that should be made very clear. Organic compounds are colored and are typically those with extensively conjugated system, typically more than 5. So, you now understand very clearly that if there are 5 or more conjugated bonds, then only the substance is likely to be a colored compound. Consider beta carotene. Now, you look at this huge structure which has a lambda max at 455 nanometer. This particular compound beta carotene has a lambda max at 455, is the far blue region of the spectrum that is absorbed. The remaining light has the complementary color of orange. So, and actually beta carotene, which is present in carrots, is orange. We know that carrots are orangish red, and the orangish red color is imparted by the compound beta carotene, and beta carotene has huge number of conjugation. So, and the lambda max is 455, which is in the visible region. Likewise, if we try to look at lycopene, it too has a very extended conjugation, and the lambda max of lycopene is 474. Now, you see that lambda max for lycopene is 474, is the near blue region of the spectrum that is absorbed, and the complementary red color is what we see. So, lycopene to us appears as a red compound, but it is actually absorbing the blue region of the visible region. So, that is to be understood very clearly, that what is absorbed is just the opposite end of what we perceive. So, if a compound is appearing red, it must be absorbing in the blue region. If the compound is appearing blue, then it must be absorbing the light of the red region. The second example that has been taken is this example of indigo dye, which is used for dyeing jeans and denims and all kinds of blue fabric. This indigo dye, the lambda max is 602 nanometer. It is in the orange region of the spectrum. This is absorbed, and the complementary color that is unabsorbed is the blue color, and that is what we perceive. So, indigo appears to be blue to us, but it has actually absorbed orange color. So, this is the concept of complementary color. What we perceive is just the opposite end of what is actually being absorbed from the visible region of the electromagnetic spectrum. Now, when we try to understand certain rules that are applicable to visible spectroscopy, one of the most common classes of colored organic molecules are the azo dyes. Azo is a nitrogen double bond with aromatic rings. So, the main part of the molecule is the central nitrogen double bond, then there are two aromatic rings, and then the aromatic rings can have substituents which are electron withdrawing groups, EWGs. From our discussion of dye substituted aromatic chromophores, the effect of opposite group is greater than the sum of individual effects. More so, this heavily conjugated system is then, now you see there is this electron withdrawing group, benzene ring, then nitrogen double bond, again benzene ring, and then again electron withdrawing group. So, the whole system is having a beautiful pi conjugation. Coincidentally, it is necessary for these to be opposite for the original synthetic preparation. So, you see that these kind of conjugated systems are synthetically prepared, although azo dyes have been banned, but they are of great significance because they are at one point of time in the dyeing industry, azo dyes were the only compounds which could provide very good coloration to all types of fabric, be it synthetic fabric or natural fabric. So, you see that they had a big market, and the beauty of the colored compound lies in the structure, and the structure had extensive pi conjugation. So, that was the beauty of these azo dyes from the structural point of view. In general, they are now considered to be environmentally unsafe. These materials are some of the more familiar colors of our environment. The para red, the fast brown, and the sunset yellow, which is used in the food, these are the structures, because these are all colored compounds and they are used for various purposes, and sunset yellow of course is a good azo compound because it is used in food industry. However, the some of the azo dyes, 16 azo dyes have been banned because they have been found to be carcinogenic and mutagenic. A huge number of such compounds can be enlisted, there is no end to these list of compounds, because the more the conjugation, the better would be the structure in from the point of view of its conjugation. Some of the common food dyes are that is a blue color, which is used in beverages, dairy products, powders, jellies, confectionaries, condiments, icing, etc., is the blue number 1, and then red orange, which is used in gelatins, puddings, dairy products, confectionaries, beverages, condiments, is red number 40. Similarly, orange common uses food dye is used in cereals, baked foods, etc. You look at the structure of the yellow number 6 and so on. So, you see that the more the conjugated system, the better it is, and that imparts color of different types, blue, red, orange, yellow, and so on and so forth. Therefore, there are certain parameters that have to be understood carefully. In biological sciences, these compounds are used as dye to selectively stain different tissues or cell structures. Even these dyes are used for staining purposes, particularly in the biological system. The Bee-Rich Scarlet is a dye used with picric acid, aniline blue for staining collagen, reticulum, muscle and plasma. Luna's method for erythrocytes and ionophil granules has also been used, and these are very important dyes which are specifically used in biological system. If we then try to understand that even in the pH range, the pH paper that has been made, there are dyes which are changing color at a particular level of pH. In the chemical sciences, where we look at acid base indicators used in various pH range, remember that you have seen the pH paper, and that effect of pH on the aromatic system is what is the science behind the generation of the pH paper, or the manufacturing science that we say. Methyl orange, which has a yellow color when it is below 4.4, actually changes to red color when the pH goes still further down to 3.2. So, just by protonation, we just learnt about protonation, deprotonation, these can change the pH, and therefore, the color also changes. So, that is where it comes to very interesting science, and many such uses are possible for these compounds, and therefore, it is a very interesting science when we try to understand the chemistry of UV spectroscopy and visible spectroscopy. Now, we come to a new chapter which is called NMR spectroscopy. It is an interesting science because here we learn about the chemical environment around the carbon chain, how many hydrogen or protons that are present, and to be able to predict the carbon chain also. That is done by C13 NMR. It deals with the radio frequency, and that is why it comes under the category of spectroscopy. Let us try to look at this. NMR is the most powerful tool available for organic structure determination. So, you see that it is not easy to be able to describe a structure by just one tool. Time and again I have told that we need the information from UV, from IR, from mass and NMR to be able to collectively then decide about the structure. It is used to study a wide variety of nuclei, that is the proton, carbon 13, nitrogen 15, fluoride 19, phosphorus 31. The nuclear spin, actually these nuclei are very special. It is not that any and every isotopic species can be used for NMR analysis. It is precisely only the proton and the C13 and the N15 and the F19 and the phosphorus 31, those only can be taken for NMR study. A nucleus with an odd atomic number or an odd mass number has a nuclear spin. So, you see that any nuclei which has an odd number, only that atomic number and odd mass number has a nuclear spin. And if the mandatory fact for this is that it should have a nuclear spin. The spinning charged nucleus generates a magnetic field. Any charge body, if it is spinning, it creates a magnetic field. That is how the electromagnetic system arises. And this is how a spinning proton creates a current and it becomes like a small magnetic bar. It is almost equivalent. The magnetic field that is generated creates that kind of a electromagnetic field. Now, external magnetic, when this small magnet is placed in an external field, the spinning proton acts like a magnet bar. So, what happens? Suppose now this is a small magnet. Now, this magnet is made to sit in another big magnet. They will have different fields. So, it will either align itself or it will twist itself. If it aligns itself, it is more stable and there is a lowering of energy. If it reverses itself, then it will become less stable and it will become energetically very high. Now, these are some basics which we need to understand before entering into the understanding of nuclear magnetic resonance spectroscopy, the NMR spectroscopy. So, with this background, we just start understanding what NMR is all about. There are two energy states for any system. One is the alpha state and the other is the beta state. Now, there is a difference of h nu or delta E between these two states when, as what I showed you, it can either align itself or it can reverse itself. So, these are the lower energy state and the higher energy state which we are comparing.